And I put sort of as a caveat underneath that. Why? Because couple of things. We want to know, first of all, what the stars are made of, but we really can't get to them, can we? The one that we can get to is the sun. So a lot of the information that we have on stars comes from the sun. However, at the same time, we have been around for a short period of time, and we have not witnessed the birth of the sun. And we will not be around to witness what happens at the end of the sun's life. To do that, we have to see the stars. So it's sort of a marriage of knowledge between those two things. And so that's why I said sort of. Let me get into that. So first things first, yes, our sun is a star, and other stars are considered suns, possibly, of their own planetary systems. However, we must be of two minds about that, because we can talk about data and how typical the sun is as a star, and we find that our sun's actually a pretty unremarkable average star. However, we have to also recognize that our sun is emotionally, historically, and geologically, evolutionarily, and physically indispensable to us. Right? We wouldn't be here without it. To us, it's the most important star in the universe. So, just like everything else in life, it's complex. Yeah, the sun's an average star, but it's also extremely important. All right, and I said I qualified, we're talking about the sun today, sort of, and I told you a little bit about why, and I told you about we're looking at stars for other information, maybe about the fate and origin of our sun. Astronomers are actually actuaries. They look out into the universe and they see stars. And they can get a huge cross-section of stars that are just being born and stars that are dying to stars that have died long ago. So everywhere you look, there's a star at a different point in its origin, in its life story. So that's why learning about the stars is one of the reasons why it's so important, is because we're finding out more about our home by looking out there. The sun has been around for about 4.6 billion years, and humans have been around for about 200,000. That's 0.004% of the sun's life. When looking at stars, astronomers not only have to take into account the speed of light and the expansion of the universe, but also their statistical variation. So it's a little complex when you're looking what I'm actually looking at and when it actually happened. It's not a bug, it's a feature. Like I said, having that statistical variation is complex, but it's giving us a lot of information about the fate of other stars and the fate of our own sun. And I mentioned before that the sun, being so close to our sun, has logistical advantages. We can sit here and observe it and look and see what's happening. We can send satellites up around the Earth to sample light and sample the solar wind to find out what's going on there. And then finally, we're actually sending satellites to the sun now to sample and understand what's going on. Our particular star that we're talking about tonight is a very sun-like model, in other words. So some of the stuff about the sun, like I said, we can't observe directly. We are creating a model. Like this just went off. Okay. And it's maybe not a stretch to consider our sun an every star, sort of an average Joe, what we see out there in the universe. Hey, I was told there'd be pictures, not just me talking, right? So let's get to that. Let's start at this picture here. It's from the Solar and Heliospheric Observatory, SOHO. I put that in this presentation yesterday, and I really wanted this morning to update it and show you what the sun looks like today, but I didn't do it, and I'll tell you why in a moment. There's the website for it. Like I said, it was current of yesterday, and it's under the heading HMI. It's what you'll be able to see with a standard solar filter on a typical amateur astronomer's telescope. And there it is. All right, what you're seeing there, if you may don't know whether you all know, but we're in a solar minimum now, and this little thing right here that you can see is a sunspot, which you haven't been able to see for months and months. They're starting to come back a little bit, and you can see them. And the reason I'm telling you now I didn't update it is because I want you guys to go home, log on to that website, and take a look at what the sun looks like now. So I left that little bit of a mind, of an ear bug for you guys to maybe take it on yourselves, go home tonight, take a look. All right, so let's talk about what's inside a star. The materials of construction, hydrogen, 71 and change, helium, 27% and change, and then metals, 1.43%. And just so everyone knows, right over here, astronomers consider anything that isn't hydrogen and helium that's an element, as a metal. So that when you hear astronomers talk about stars with lots of metals in it or little metals, they're talking about anything that isn't hydrogen and helium. Metals isn't really satisfying for us, though, is it? So let's talk a little bit about it. Here is the sun's spectrum. So these lines are called absorption lines, these black lines. And those happen when metals or any element absorbs light, and the electrons in the element absorb the light when they move from one position to another, and that's why you get those black lines. So that's how we can tell what's in a star's photosphere. And then here, and you can't read the lines on this chart here, but this is actually helium and hydrogen are up here at around 10 to the 12th as far as the relative amount of helium and hydrogen in a star. And over here at the larger atomic weights are elements in around 1. So it goes from 10 to the 12th numbers of atoms to about 1. So that tells you it drops off significantly how much helium and hydrogen is in the sun compared to other things. All right, let's play a little bit of a game here. Here's the core temperature of the sun, around 1.56 times 10 to the 7th degrees Kelvin. Does everyone remember what Kelvin is? Kelvin's an absolute temperature. It's Celsius, but minus 200. Celsius is the same thing as Kelvin, but 273 degrees higher. So water freezes at 273 degrees Kelvin and boils at 373 degrees Kelvin. So that's pretty hot. All right. So if you can think about, like we just gave, water at freezing and boiling point as a comparator. So maybe you can do that for some of these other. Core pressure is 1.97 times 10 to the 11th atmospheres. What do we know that's an easy reference point for atmospheres? The atmosphere. The atmosphere is here at Earth at sea level is 1 atmosphere. So the mass, let's go through these a little quicker. Mass is close to 2 times 10 to the 30th. The diameter is 1 million and change in kilometers. The distance to is about 1.496 times 10 to the 8th kilometers. That's about 93 million miles. A couple of other distance units there. That equals about 1 AU. It's actually not about, it's exactly 1 AU. That's the definition of an AU. It's the distance from here to the sun. And then a light year, it's 0.0, it's 0.4016. And then the energy it puts out is 3.8 times 10 to the 26th. So what is the sun really? What do all those numbers mean? It's an incredibly hot, incredibly massive, and it's under gargantuan pressures. It's not made up of matter that we experience here at all on Earth. It's actually a fourth state of matter called plasma. There is some regular matter that in the form of ions in the atmosphere and on the surface, but otherwise it's mostly plasma. The plasma is made up of hydrogen nuclei, which are protons, because hydrogen has an atomic number of 1, if you remember. So there's 1 proton in there. That's what happens when you strip all the electrons away from it. It just becomes a proton. The helium nuclei, which are 2 protons and 2 neutrons. So there's 4 little guys in there, and then a whole bunch of free electrons. The plasma acts as a fluid even when it's extremely dense at the core of the sun. It's so hot down there that it still moves around like a fluid, even though it's 10 times the density of lead. Here, there we go. Here's a picture of the sun. These are the internal portions here. You have the core, which was where all that interesting data was coming from. You have this radiative zone. This radiative zone, the heat goes out there just as it said, it radiates from there. It just travels kind of in a straight line. The actual photons do not travel in a straight line. We'll get to that in a little bit. Then there's this convective zone where the plasma is boiling, it's moving around, it's rising, it's boiling like it would in a pot on your stove. The cool stuff is going down to the bottom, the hot stuff is coming up. Then there is the photosphere right here, which is the surface of the sun. Then we have, on top of all that, the photosphere is kind of considered the surface, although the sun doesn't really have a surface. Then we have the chromosphere, which is part of the atmosphere. There's the corona, which is part of the atmosphere. And then you have some features here like prominences and flares and sunspots. The sun is a magnetic dynamo. We talked about that radiative zone in the core. That's this guy here. The sun rotates. When the sun rotates, and you have all those ions there in the sun, or the various charged particles in the plasma, I should say, in the sun, this guy rotates differently than the outside. The outside has a differential rotation. That means by the equator, it rotates faster. By the poles, it rotates a little bit slower. This core and radiative zone here in the yellow, well, that guy spins monolithically. All right? So you have that difference of rotation, and what does it do? It takes these magnetic lines and it starts to stretch them like this. and this happens over an 11-year cycle. There we go. The solar cycle is 11 years long, from solar minimum to solar maximum, and then back again. It was originally discovered by the solar cycle by recording the frequency of sunspot activity, flares, sunspots, and CMEs, and coronal holes. Some of those features that we showed on the sun, they're all phenomenon that vary with the solar cycle. It's important to study and predict solar events and the space weather to protect not only our astronauts up in space, but also our infrastructure here on Earth. Some of those solar events can actually create damaging currents in our own power grids and things like that. And then also we are increasingly dependent on satellites around our planet. All right, a star is born. So please be quiet for the next few slides. We don't want to wake the baby stars. There's a stellar nursery. There's another one. And as you can see, they look like... here's actual... in the center here, this is actually a protoplanetary disk. The suns are little dots in the center there, and that's planets forming around those suns. So what is a stellar nursery? It's a cold, dense, massive nebula, which is just a big cloud of molecular hydrogen, mostly. Cold means it's about 10 degrees above absolute zero, 10 K. Massive means it's tens of light years across. That size and that density protects the inside of those clouds from disruptive cosmic radiation. Those regions then have so much matter all together in one place can collapse spontaneously because they have, even though they're spread out, they still have gravity. And so that dense region, if it's cold enough and protected like that, and it meets the Jeans mass, which it compares the mass of the clump of cloud to the pressure that the cloud exerts outward to prevent collapse. So if it does meet that Jeans mass criteria, it will start to spontaneously collapse. Collapse can also, however, be assisted by perturbations from external events. And those external events could be a passing star, a nearby energetic event, or cloud collisions. Once that happens, a protostar begins to form. What are protostars? Those are stars that have begun collapse, but they haven't started nuclear fusion. And just so everyone knows, right, nuclear fusion is what is running all the stars. Remember the conservation of the energy. So remember that's a law that we may have learned way back in grammar school, right? Maybe in high school or in college, depending upon what you studied. And it's a potential. So if you remember this terminology, potential energy, that's the gravity energy, gets converted. It gets converted to kinetic energy, which is the motion of the gas moving in or rotating, and that increases as the gravity energy gets converted, and enthalpy, which is heat energy and pressure energy, also increases. So as the potential energy gets converted, it gets hotter, and the pressures start to climb. If the protostar is massive enough, eventually hydrogen fusion or burning can be sustained. At that point, collapse is halted in the protostar, hydrostatic equilibrium is reached, and a new star is born. We're going to come back to hydrostatic equilibrium. There it is. So here in this chart you have all it's showing, I know it's difficult to see, but you have arrows pointing out from the core and arrows pointing in. So what's happening? The plasma pressure, remember those big pressures in the core we went over in the beginning? Pushing the star outward. The gas doesn't want to be that close to each other. Gravity's pushing in. Fusion is heating that core up to those huge temperatures that make that pressure happen. But why is it stable? Why doesn't it blow up? You know, what happens if the fusion changes a little bit, or the star gets a little bit more material? Why doesn't it blow up? Well, remember that a collapsing fluid heats and an expanding fluid cools. So that's the safety valve on a star. Changes in the rate of fusion are opposed by changes in the plasma expansion. If it gets hotter, the sun will expand, the gas will cool, and then the fusion starts to slow down. Vice versa on the other side. Powering a star. Sometimes how a star is powered makes sense. This is the kinetic energy. It's how fast a particle is moving inside the core. At certain temperatures, it's not a distribution. I mean, it's not just one speed. It's a distribution of speeds. Some particles don't move at all. Some particles all the way on this side move very, very fast. So that makes sense. All right? The particles in blue here have enough speed for 2 hydrogen protons to bang together and form helium. However, sometimes it's also a head scratcher. The electrostatic repulsion of like charged particles, remember we're talking about 2 protons here, so they're both positive charge. They actually did that math out and determined that it would dictate a much higher thermal energy than is available in our sun for fusion to actually happen. However, the smallest things of matter, protons and things much smaller than that, actually behave quite weirdly. They can behave like waves. Small particles can change their position without moving through space. Basically, they're teleporting. I have to move from here to here. I have to walk there. That's not what these particles do. They'll just transport. And so that mechanism is called quantum tunneling, and quantum tunneling is what's required to actually get those protons together. That weird behavior of particles. The higher kinetic energy a particle has, the more likely it is to tunnel. So that curve is still valid. It's just being helped by quantum tunneling. And quantum tunneling is required to make fusion go. It's a real thing. And conversion. So what's happening? Remember, E equals mc squared. That isn't just a calculation. That's actually telling you the truth. Energy and matter, that's mass there, that's energy, are the same thing. Matter is just a form of energy. And so you can convert between the two by multiplying there by the speed of light squared. In the sun, 700 million metric tons of hydrogen is converted to helium per second by the sun. 5 million metric tons of matter gets converted to energy per second. Not all of the matter when fusion reaction happens gets converted. Actually, a very little bit of it does. It's 0.7%. And remember, the sun is 1.9884 times 10 to the 27 metric tons. So even though these numbers are huge, this number is huger, and so therefore there's still enough material in the sun for it to go burning on like it is for another 7 million years. All right, so this is the proton-proton chain, and I wanted to go to a little bit of detail into it. But so this is the main reaction happening in the sun, but I'm running long, so I'm not going to go too much detail into it. This is the CNO cycle. This is another fusion reaction in the sun. This is also happening and producing energy in our sun, but it is not the main reaction. It's producing about, I think it's less than 2% of the total. Suns that are 1.5 times the mass of our sun, this chain is the predominant way the way those stars operate. Let's go into the sun's various classes. Where does our sun fit into the rest of the stars? What we can't know. We cannot know by looking at a star at its brightness how far away it is from us. Why? Because the star we know the star's brightness from where we're sitting, but the star's brightness depends upon how far away it is from us. It's an inverse square relationship. The further away it is, the dimmer it will look. Stars' brightness can be classified, and the way most astronomers refer to the brightness of stars is magnitude. Stars' luminosities can be classified as a unit of power, like our sun. If we know its absolute magnitude or its luminosity as opposed to its brightness, then we can say something like we know it in watts or know it in absolute magnitude. And all absolute magnitude is the brightness of a star at a specified distance, and that specified distance is 10 parsecs. What we can know is that we know that black bodies, stars are black bodies, irradiate with color intensities with a predictable curve. We know that we know those curved shapes, and we know the surface temperature of those black bodies, spectral type and luminosity class from those curves. And once we know a star's mass from the surface temperature, spectral type, and luminosity class, then we know lots of properties about stars. And then we can know the distance and the those other things. So remember just wanted to remind you of this is a spectra with absorptions lines in it. And this is actually those curves I was talking about, telling you different, if we can take points along these curves and say, oh yeah, that star has this curved shape, then we know that that temperature is 5,000 degrees K. So what do we know from the, so we can take those curves, and now we can classify the stars based on those spectral lines we saw, based on that color curve, and we can give them a class. And here they are. The classes O, B, A, F, G, K, and M. These are the lines that you saw in the spectra here. Those are various absorptions. Those are the element and the electron transition of that element. The colors of those stars, and you can see just like a rainbow, it goes from blue to red. That color index there is those points that we took to take the shape of to identify the particular curve that gave us the class. And here are those temperatures. They range from 50,000 down to 5,780. That all gives us an HR diagram. And what is that HR? That's the Hertzsprung-Russell diagram. Up here is the spectral class, and over here is the luminosity. And so they took a whole bunch of stars. What you see here that's sort of fuzzy looking, that's actually a bunch of dots that are all stars. And use this line here, all stars that are burning hydrogen appear along here. Every single star that is currently fusing hydrogen is along here. So now we've identified the star, its mass, its luminosity. We can start to calculate its distance and a whole bunch of other things. So what's this? And what are these over here? And what are these? This line here is called the main sequence. Hydrogen, like I said, hydrogen burning stars. The sun is classified as G2, and that's a Roman numeral 5 at 5,778 degrees K surface temperature. These are other luminosity class stars along here. What are they all really? These are the end states of stars. So stars that are no longer burning hydrogen or fusing hydrogen, they are now on their way out, and they appear along here. And these are actually white dwarfs. Those guys are already gone. What will happen to the sun? What are red giants and supergiants? When the sun uses up its hydrogen fuel, it will collapse until its core gets hot enough and begins to fuse helium to carbon and oxygen. More massive stars will repeat this process. Where it stops depends upon its mass, how mass the star is. Like I said, our sun will do the hydrogen, helium, carbon, oxygen thing. But more massive stars will do neon, magnesium, silicon, and then all those various elements are burned in concentric active cores found inside the massive stars. Successive fusion types require hotter temperatures and give off more energy. The sun or star will expand to become a red giant or a super red giant. Ours is a red giant, and more massive stars, red supergiants. However, the last element on the hit parade there is iron. Regardless of mass the star's mass, fusion will stop at iron. Iron fusion just simply does not happen in the core of stars. Once the fusion stops, regardless of whether it finished burning fuel and didn't have enough temperature to continue up the scale there, or whether it reached iron, the fusion does eventually stop. The hydrostatic equilibrium that was holding up the star is now gone, and the sun or star will collapse until something stops it. What besides fusion will stop a star collapse? Electron degeneracy holds up white dwarfs. And what's that? Again, those are small particles. They behave weirdly. They have quantum properties, and those properties have a weird thing called have a weird thing happen to them called Pauli exclusion. Two particles with similar quantum values have to stay separate. They're not allowed to occupy the space close to each other. The free electrons in the plasma will start ordering themselves and provide a back pressure to resist gravity. What results there from that electron degeneracy is a white dwarf. That's what our sun will become. If electron degeneracy isn't sufficient at just under 1.5 solar masses, the star continues to collapse. Neutron degeneracy then holds up neutron stars. So if it passes electron degeneracy in a white dwarf, it continues to collapse into a neutron star. And neutron degeneracy is exactly like electron degeneracy. Neutrons are excluded from occupying like states, just like electrons are. However, why can neutron degeneracy hold up a little bit more mass? That's because of it gets an additional boost from the strong force, one of the other forces that you may have heard of besides gravity and the electrostatic force, the electromagnetic force. And then though that between 1.5 and 3 solar masses, those stars are held up by neutron degeneracy and become neutron stars. Beyond those two opposing forces, I've got nothing, and neither does the rest of the universe. The star remnant will continue to collapse and will form a black hole. Do not go gentle into that good night. This is so when those things are happening to the stars in the end state there, becoming a white dwarf, becoming a neutron star, or becoming a black hole, obviously the star doesn't like that too much. The star will blow up and become a supernova in the cases of very large stars. Most likely the star can become a planetary nebula like this, where the atmosphere is just thrown off of the sun. So as it's going through all those violent changes in its core, it's also throwing off its outer layers into the space around it. This is the Ring Nebula. This is the Crab Nebula. The Ring Nebula you might be able to see tonight in one of the scopes. I just want to urge everyone to join an astronomy club, and I want everyone to also to stay safe. As Matt had mentioned, the scopes will be open. There will be screens and or for everyone to look at, and we'll be looking at hopefully the planets and maybe even the Ring Nebula tonight and other stars and stuff. Are there any questions? Well, thank you everyone for your attention. Sure.